There are moments in the history of computing when a new machine does more than increase speed. It changes the kind of question scientists are able to ask. Quantum computing is approaching one of those moments. In December 2024, Google introduced Willow, a quantum processor containing 105 qubits. The announcement attracted enormous attention because Google reported a result on a specialized benchmark called random circuit sampling that took Willow less than 5 minutes to perform. The comparison was deliberately dramatic. Google estimated that a state-of-the-art classical supercomputer would require roughly 10 septillion years to produce an equivalent result under the assumptions of the benchmark. That number sounds almost impossible to comprehend. 10 septillion years is vastly longer than the current age of the universe. But there is an important detail that often disappears in sensational headlines. Willow did not suddenly become a machine capable of solving every difficult problem in 5 minutes. The benchmark was specifically designed to demonstrate a quantum computational advantage. It is not a practical calculation such as designing a new medicine, predicting the weather, or instantly breaking every encryption system. The real scientific achievement was different. It was a demonstration of how quantum hardware can perform a particular type of computation in a regime where classical simulation becomes extraordinarily difficult. To understand why this matters, we have to leave ordinary computing behind. A conventional computer stores information using bits. A bit can represent either 0 or 1. Billions of these simple elements can be combined to perform enormously complicated calculations. Quantum computers use qubits. A qubit is governed by the rules of quantum mechanics. Before measurement, its state can involve a combination of possible outcomes. Multiple qubits can also become entangled, creating correlations that have no straightforward classical equivalent. This does not mean that a quantum computer simply tries every possible answer simultaneously and then reads out the correct one. That popular explanation is misleading. Quantum algorithms carefully manipulate probability amplitudes. Through a phenomenon called interference, unwanted computational paths can be suppressed while useful outcomes are amplified. The challenge is designing the calculation so that this interference produces something useful. And there is a fundamental problem. Quantum information is extremely delicate. Heat, electromagnetic disturbances, microscopic imperfections, and interactions with the surrounding environment can introduce errors into a quantum computation. The more qubits a system contains, the more difficult controlling those errors becomes. For years, this problem represented one of the biggest obstacles standing between experimental quantum machines and genuinely scalable quantum computers. That is why Willow's most important result may not be the enormous time comparison at all. It is error correction. Google reported that as the number of physical qubits used in its error-correcting system increased, the logical error rate decreased. In other words, adding more hardware to the error-correcting architecture produced a more reliable logical qubit rather than simply creating an even larger collection of noisy physical qubits. This is a crucial milestone because useful quantum computing will require enormous numbers of physical components working together to protect much smaller amounts of logical quantum information. Imagine trying to preserve a whisper inside a stadium filled with noise. Adding more people does not normally make the whisper easier to hear. Quantum error correction attempts to use carefully structured redundancy so that the fragile information can survive despite individual components making mistakes. Willow represents progress toward making that possible. But this is also where the story becomes much more interesting than the usual "quantum computer beats supercomputer" headline. Quantum computing is forcing scientists to reconsider what computation actually means. A classical computer represents information using physical states that we can describe with familiar logic. A quantum processor operates according to a different mathematical framework. Its behavior is determined by probability amplitudes, entanglement, measurement, and interference. None of this requires another universe. And Willow has not demonstrated that a calculation is being secretly performed in parallel universes. The idea that quantum computation somehow distributes work across alternate realities is connected to interpretations of quantum mechanics, particularly the many worlds interpretation. But interpretations are not experimental evidence that multiple universes are physically carrying out pieces of a calculation. This distinction matters. The science is already extraordinary without adding a multiverse claim that the experiment does not establish. What Willow actually demonstrates is that carefully controlled quantum systems can enter a computational regime that becomes extraordinarily difficult for classical machines to reproduce. That alone is profound. It means the future of computing may not simply involve building conventional processors with more transistors and higher clock speeds. Instead, some problems may eventually require machines that exploit the fundamental behavior of nature itself. The potential applications are still being investigated. Quantum computers could eventually become useful for simulating molecules, studying materials, optimizing certain complex systems, and exploring physical processes that are difficult to reproduce with conventional computers. But there is a long road between demonstrating quantum advantage on a specialized benchmark and building a fault-tolerant machine capable of solving commercially important problems. Willow does not mean that era has already arrived. It means researchers have taken another important step toward it. And perhaps that is the most fascinating part of this story. For centuries, humans have built tools by learning how nature behaves. We learned to control fire, harness electricity, manipulate atoms, and eventually engineer individual quantum states. Now we are attempting something even more delicate: constructing machines whose operation depends directly on the strange rules governing matter at the smallest scales. The machine may fit inside a laboratory. The physics behind it does not. And as quantum processors become larger, more reliable, and better protected from errors, the most important question will not be whether they can produce astonishing benchmark numbers. It will be what useful problems we can finally make them solve. And as quantum processors become larger, more reliable, and better protected from errors, the most important question will not be whether they can produce astonishing benchmark numbers. It will be what useful problems we can finally make them solve.